Hello and welcome to GOTO Book Club once again. My name's James Lewis. I'm a director at Thoughtworks, and today I'm delighted to be talking to Unmesh Joshi about the release of his new book and the patterns within it, Patterns of Distributed Systems. Unmesh, would you like to introduce yourself to the audience?
Yeah. Hey, folks. My name is Unmesh Joshi, and I work as principal consultant at Thoughtworks. Been with Thoughtworks close to 16, 17 years now. And last several years, I've been thinking and writing about distributed systems. We'll cover more of that, I think, as we talk.
Yeah, and so I mean that's a fairly long time to be with it in a consulting organization. Can you tell me a bit about the background, maybe some of the experiences that led you to become interested in distributed systems, and the sort of experiences you've had that led you down this path? Because I mean, frankly, this is a lesser trodden path in the software engineering literature. Certainly, the sort of the more sort of, I guess, user friendly literature, because it's regarded as a really difficult topic. So, what were the experiences that led you to this?
Oh yeah, it was a interesting journey, I would say. So, I mean, as I think any professional for last several years working with cloud, I mean, you see services and products you use on cloud or even in your data centers that are distributed by nature, right? I mean, you use Kafka, you use even simple things like Amazon S3. And I had been using, like everyone else, some of that. And I was always like curious. I mean, why now and why they are designed the way they are? But I never spent more time on going in depth or in details until the point where like around, I think, 2017, I got a chance to work on a very interesting project. I mean, so we were involved in developing software for an optical telescope, and that's going to be one of the largest telescope once it goes live, called 30-meter telescope. Naturally, because it was a telescope ecosystem, the software that we were developing, I mean, we could not use off-the-shelf products. I mean, we used frameworks like Akka, but we had to do a lot of framework development ourselves. And it turned out, just because multiple telescope subsystems need to coordinate and you need to keep data that's highly available and also consistent. What we were building turned out to be a distributed system. And at that point, I mean, I kind of had to go in depth of how these things are built and how they work. And all the literature, I mean, the books and academic papers that are out there, I mean,
I mean, you're essentially going back to Lamport, aren't you?
Yes. And we'll talk about Lamport's, I mean, Paxos and other things. But a lot of that, I mean, it took a lot of, I mean, you need to stretch your imagination when you read something, and then you go and say, start writing Java code. I mean, how do you map things? And what I started doing at that point was, I mean, I think, I mean, to test if you really understand something is to write code and to run that in production. I mean, that's the ultimate test always. But then I thought it might be easier if I look at code that I mean, there are a lot of open source frameworks out there like Kafka and Cassandra and stuff like that. Those are open source tools, and they are battle tested in production. So why not go and look at their code and start to make sense, try to make sense out of it, and see what the building blocks look like, so that it's also a good validation of some of what we are building, if it matches with some of the decisions that are taken there as well. And to start with, it was hard, obviously, because you can imagine you open a Cassandra code base you don't know where to start, really. So what I started doing was, I just thought, if I need to build Kafka-like thing, what all things are needed, and maybe look at some of the earlier versions of Kafka. And it's, it's good thing with open source that you can go through the commit history, and generally you see that some of the earlier versions of all these complex products, they are simple, because and easier to look at. So I went through those, and I tried building my own miniature versions of these products, and that naturally, because I looked at multiple of these, I could figure out that, okay, there are similar things happening, even if not exactly the same. There are similar building blocks in code that are that you see. And I just happened to talk to Martin Fowler about it, that this is the approach that I'm taking in for learning how distributed systems work, and I also tried teaching using code, because we were attempting to teach more developers about distributed system concepts, and we also had some college professors taking sessions for our developers, but it never worked well, because as I said, there is a gap between the theory that you learn and the code. So this more code-driven approach of, if you need to build something that is a distributed key value store, let's say, what building blocks you need to think of, and how they look like in code, and that worked pretty well. And that's when Martin thought that, I think patterns approach is probably a better, because you see things which are similar but not exactly the same. But they cover a broader range, broader range of implementations out there. So that's how it started, really.
You touched on a number of things I find quite interesting there. I remember a conversation I had some years ago with Brian Getz about the Java concurrency book he wrote. And I was sort of amazed at how he got into it. I was like, oh my God, because it became the Bible, right? If you're working in multi-threaded systems in Java, everyone had that book on their shelf. I said, Brian, how did you, how came you to write this book? Were you this massive expert in concurrency? And he actually said, no. It turns out I wanted to learn how it worked. And so I thought the best way of doing that was to actually start writing the stuff down and start writing down, start writing code to work out how it worked for myself. And it turned into the Java concurrency book. And it seems like a very similar thing that you've got going on.
It is.
Curiosity, really.
Yeah. It was more like demystifying some of the words that you read Lamport's clock, and you want to see, how does that look in code, and where it's used.
Yes, because we jokingly mentioned the Lamport's papers earlier, a minute or so ago, and actually, they genuinely are actually that them and the Liskov papers, and going back almost like 2 generations of software engineers now. They really are, but also they're academic. They're academic in nature, so it is fascinating how you've taken those ideas and actually brought them into a form that some regular Joes like myself, regular software engineers like myself can understand, right? It's a pretty staggering achievement, I have to say, Unmesh. So first of all, thank you from everyone for doing it. The other thing I think you talked on there, which I thought was quite amusing in a sense, was this idea that I think it's a very it's typical of many of our colleagues. I think it's one of the reasons I think I love working in Thoughtworks, which is this idea that the way you really get to understand something is by turning it into code and running it in production. It's almost like Richard Feynman, the Nobel Prize winning physicist, he used to say about the way you understand something is by teaching it to others. I guess this is like the strong version of teaching it to others, right? It's actually you're teaching it to the teacher, right, where there is no misunderstanding,
Oh yeah, absolutely. I've seen it so many times, and maybe it's just me, but I've seen it with most of the professional developers, that you understand things, and that's maybe the nature of software development itself. That there's a limit to how much you can specify and imagine things on whiteboard, and maybe with some abstract concepts. Finally, when you write code, you get more insights, and then you can reflect on those insights, and then maybe go back to specifications and stuff like. I mean, that's just the very nature of software development, I think.
So if we were to, I guess, come back to basics, right? So when we say distributed systems, what do we mean when we say distributed system? What makes? I know maybe it's a silly question, but I mean, let's come right back. And when we say distributed system, what is that? What does that entail?
Well, I mean, that's a great question. I think because people interpret distributed systems with their own context. I mean, microservices ecosystem itself can be called as a distributed system as well, and Kafka is a distributed system as well, and cloud is a distributed system as well. So I mean, what I primarily have focused on is essentially when you have data systems. I mean, you need to maintain state, and you need to maintain it on multiple servers to make it available, and then you need to make sure that that state is consistent across servers, and whatever systems, and obviously you need to shard or partition that state so that you can have lots and lots of data stored and processed. So I think what I have focused on is on this kind of systems, and things like Kafka, Cassandra, Amazon S3, Cosmos DB, and I mean all the data things.
So really, we're talking in terms of cat theory, when we're talking, and correct me because I might be wrong here, but in terms of cat theory, we're talking about consistent systems, as opposed to available systems.
Yeah. And there is always a balance. I think that that all these systems, they like Paxos, for example, also is available as long as the majority of the servers are available. But beyond that, it will just favor consistency.
Cool, thank you. And so, maybe let's talk about. You mentioned briefly about patterns. Why did you go for the patterns approach to start with? Why not just go for writing your own piece of software essentially? And why not release your own Kafka, right? And say, look at that.
I mean, so patterns I thought was a useful approach, because let's say if you have to build something like Kafka, the concepts that you need to know or need to implement, there is a lot of similarity between, for example, when you implement something like Cassandra. I mean, even if not exactly the same, or you are implementing something like etcd, which is a Raft implementation. There are a lot of common concepts between, say, Raft and Kafka's replication mechanism. So patterns approach, what they allow you to do is talk of this similar concepts that span across multiple implementations, and then they become more useful, I think, because once, for example, there is a concept of let's say high watermark, that when you are replicating a log, you need to really demarcate which portion of your log is like stable, it's not going to change, and which portion is volatile. I mean, it might change if your nodes crash and leaders change and stuff like that. Now, that high watermark concept, whenever you use log replication, like in Kafka, is also there in Raft, which is called as a commit index. And whether you use some other replicated log algorithm like view stamp replication or multi-Paxos, which no one has documented how it's implemented, but you need
backward at this point, right?
But you need some concept like that, and once you know what that concept is and how it's typically implemented, you read a Raft paper or a view stamp replication paper or or Kafka's replication mechanism, you know what's going on, and you can connect the dots.
So you mentioned Raft and Paxos. Obviously, these are names that people have heard bandied around, or different mechanisms for staying consistent, et cetera, et cetera. So, just to put you on the spot, here you go. Describe the differences between Raft and Paxos for us.
Oh yeah, absolutely. And I think that's important, because you see that Paxos, the Microsoft and Google folks and all the services they always mention that they implement Paxos for replica consistency, and all the open source world says that they implement Raft. And if you read Paxos paper, the original Paxos Made Simple or other papers, what it describes is what is called as a single decree Paxos, like how multiple nodes achieve consensus on a single value.
Right.
So in the literature, what's understood as Paxos, and I have actually documented that as a pattern. So I've documented Paxos as a pattern because we thought that concept that you need two phases to reach an agreement between nodes. Then you use majority quorum to make sure that the decision taken by the previous quorum is visible whenever you try next. And you have something called as, what I have documented as a different pattern called generation clock. So you all this coordination is done by a leader, which is called as proposer in Paxos. And you mark the leadership with monotonically increasing number, so that if there are, you always tolerate multiple leaders, but you can always cut off older leaders. So you only the latest leader can make progress. So this basic mechanism of how to combine these concepts of epochs or generation clock, two-phased execution, and then recovering from, let's say, partial writes, Paxos documents that, and how to do that for, let's say, a single request or a single value.
You mentioned something. Do you know if I just interrupt? Because you mentioned something really which we should probably, maybe this is not the right time, we can come back to it, but you mentioned something like the latest, we tolerate multiple, but the latest. And that cuts to the heart of the problems with distributed systems, doesn't it?
Yeah, we'll talk about, so that latest comes in in various different areas of, so what is the latest value? In terms of Paxos, when I say latest leader, what is the leader that has just won the election, let's say, which has the latest epoch or the latest generation clock, and it can be the only leader that can make progress. So these concepts, how they work together is documented in Paxos, and in literature mostly it's documented how to do that for a single value or a single request. But obviously one of the side effects or one of the issues with this basic mechanism is what you can call as initialize once. So once you reach an agreement, you cannot have another request or another value that can be chosen. So it becomes immutable after that. And that's, even if it's a good way to understand the basic mechanism and how to structure that basic mechanism to reach an agreement. Yeah. It's not very useful in practice if you have to build a database, for example, because you need to update values multiple times, and if you maybe execute requests like register release in when you implement something like etcd, and the mechanism to do that essentially is to arrange all your requests in an ordered log. And you can imagine again that if you execute this basic Paxos mechanism on each entry on this ordered log, then you know that all the nodes will reach agreement on each entry. And then if they execute these requests and follow that log order, they will execute all the requests in exactly the same same order, and then they will reach exactly the same state. So obviously this basic Paxos mechanism, like two phases and establishing a epoch by quorum voting,
Yeah.
it's not very efficient naturally. If you do it every time you get a user request, and you need to optimize that for any production implementation. And generally that's what happens in practice. I mean, whenever someone says that they implement Paxos for implementing, let's say, replica consistency in their database, mostly they are using something like a replicated log mechanism.
Right.
And that replicated log mechanism essentially then combines this basic Paxos to elect a leader at startup.
Yeah.
And then all the requests essentially are ordered in the log. This single leader does that. So it's not like for every request you go and try to establish a leadership.
Yes.
And then it also combines things like high watermark that I talked about, that you demarcate your ordered log so that you know what is the stable portion of the log and what is the not so stable portion. And Raft essentially details out how to do that with all the nitty-gritties in the implementation.
So essentially, Raft is an evolution towards practicality.
Practicality of
the basic Paxos algorithm. When I say basic Paxos algorithm, it's not basic at all. Yeah, I mean, it reminds me. I think I shared with you previously an article that James Mickens, the former Microsoft distributed systems researcher, wrote for Unix magazine on Byzantine generals and new Byzantine generals algorithms are popping up all the time, and how, frankly, they're really simple. They're not simple.
Pretty simple. Oh yeah, absolutely.
It brings me actually. I mean, because you talked about a couple of things there relating to. Well, I mean, in my mind, relating to time, and I think that's something crucially we should probably talk about, because it's at the heart of the problem with distributed systems, isn't it?
Oh yeah.
How you manage time across multiple different processes, multiple different systems.
Yeah, absolutely. And very interestingly, I mean, as you know, Google has this timing infrastructure called True Time with atomic clocks and GPS and stuff like that. I mean, good thing to know is that even with atomic clocks and all the infrastructure that Google has, when they have data centers across the globe and servers span so far, they cannot get exact clocks exactly matching. So there is always a delta. And what essentially Google does is make sure that delta between two clocks is minimal. So it's 7 milliseconds, I think, is what they guarantee. But essentially, practically, it is not. I mean, you will never get two servers to agree on same time, and that's one of the big issues. And I mean, obviously, Lamport clock is one way, and I have documented in the book how Lamport clock works. I mean, you essentially just maintain an integer, and you pass along that integer with every request, and then every server receiving the request also keeps track of what value it's getting and what is the value that it has. And when I'm saying, I mean, typically in databases, you can imagine if it's a key value store or let's say even your document store, your document is considered, you can consider as a value, or in your RDBMS, your row, you can consider as a value. So you store this version with that value, or with the primary key, or with the key of that value, and then comparing these values, these keys or these numbers attached to the keys, you can figure out which update happened before another one. I mean, that's a simple Lamport clock mechanism. Now, as you can imagine, in databases that we all use, if we have to compare integers to know which values are ahead and later, it can be quite confusing. So most databases combine this technique, this basic Lamport clock technique of tracking the integer with actual date and time that you get on your servers, and that's called as hybrid clock. So most your databases like MongoDB and YugabyteDB and CockroachDB, I mean, you see that in practice they use something called as hybrid clock.
Right.
And that allows you to combine this system time with this integer that can track which values are greater after the other. But yeah, I mean, it's fascinating, and I think it's something that people will find exciting when they read in the book how this is typically implemented. I mean, there is a simple Java code that I have in there.
You mentioned Spanner. I remember maybe our friends at the book club at GOTO can dig this out and add it to the notes, because I remember seeing some of the Spanner engineers talking about it. Oh, so you talked about True Time, and Cloud Spanner is the database implementation that makes use of it.
One thing to add there, so just an example of how this patterns approach is useful. I mean, what's done in True Time or with the use of True Time in Spanner is essentially that you get this, let's say, maximum delta between two clocks. I mean, how much clock values
how much
differ.
drift there is, essentially, right?
Yeah. And then how you can use that essentially is to, if you are writing a particular value at a particular time, let's say you are writing a value at time 5, and you know that it will take maybe 500 milliseconds to, I mean, I'm just giving an example value. 500 milliseconds is too high to wait. But within 500 milliseconds, all the other servers in the cluster are going to get that 5 p.m. as the value. So what this writer does is it waits for 500 milliseconds just to make sure that everyone else has that clock value or time value, and then it makes that value visible, or then it writes that value at that timestamp. So if you can, if you know how much that maximum skew between or across servers in cluster can be, then you can implement it without True Time as well. I mean, that's what most of the open source databases do. I mean, they assume that maybe the clock skew, the max drift, maybe 200 milliseconds within your AWS cluster, and then they can just implement that weight for 200. I mean, True Time just makes it more practical, saying it won't be more than 7 milliseconds, so you can actually wait for 7 milliseconds. It's not
it offers you a guarantee, essentially.
Yeah.
I mean, I remember the talk, and it was a fascinating talk they gave. They had this quite amusing sort of portion of it when they were talking about cat theorem again, back to cat theorem. And they were talking about how they are consistent and available. And they said, oh, it turns out we've broken cat theorem. That was the start of the talk. And then at the end of the talk, they said, actually, we haven't broken cat theorem at all. It's just that we never partition. Our networks are so good that we just don't partition, which I thought was quite an amusing kind of appendix at the end of the talk.
Yeah, I mean, it's tricky understanding things at implementation level. I think how it helps is you get this kind of intuitive, and I mean, even if you don't read specifications and you don't know exactly how these things work, you get this intuitive understanding. So if something breaks in production, for example, and you need to make sense of what might have happened, you at least have some pointers Like this, and I've given this example, and I think a lot of people give this example, that there was this Cloudflare outage, I think a couple of years back, and the outage was essentially because the HCD server that they were using, there was outage in that. And then there is this inherent issue with Raft's leader election. And I mean, it can very well happen with any basic consensus implementation, that you just keep on electing leader and no one can make progress. And that's I mean, it can very well happen unless some care is taken. But if you are aware that, okay, something like this might happen. I mean, it might happen in your Kafka cluster, or it might happen in your Kubernetes cluster as well.
Right.
We are all fortunate that we things don't fail that often.
It's talking about failure, because I mean, failure is, I think, one of those. I mean, the edge cases in these systems are, I mean, there's lots of them, and they're pretty sharp.
Oh, yeah.
I mean, know, sharp edges. And I don't know if you've come across. I'm sure you have come across the Jepsen suite of tools.
Yes, absolutely, yes.
Which are useful. I mean, that's provided me with hours of entertainment over the
And I think I mean, just to compare the patterns approach with, so Jepsen, I mean, it's an excellent tool, and it takes a black box approach. So it treats your products as black boxes, and then it runs some tests and introduces failures in between. And in patterns is, I mean, you can think of it probably as a white box approach. So you know what the building blocks look like. You can maybe think through some of the issues that you might face.
Well, I think probably you could look at the failures that Jepsen detects, and then you could describe them in terms of failures in a particular implementation of a pattern, can't you? I mean, that's
absolutely.
And I guess that comes back to the actual implementation, right? So it comes back to the fact that the book is rooted in code. It's rooted in actual code that is executable, is unit testable, and you can inspect yourself. I think that's a really important part of the book, isn't it?
Yeah, absolutely. So and that is the reason I think. So before writing each of these patterns, I had actually working Java code, and Java as a language I chose, I mean, just because it's more people familiar with it. And it's a simple language. There is no other reason.
Even the C# people are familiar with Java.
Oh, yes. And then I made sure that I explained pattern around this basic Java implementation that's out there, and tried not to use pseudocode to explain the code structure.
Maybe we should chunk up a little bit now, because I mean, we're in the weeds. We're talking about clocks. We're talking about, not in the weeds. We're in the details, right? And which for me is the fascinating part of all this. But I guess we can maybe take a step back, because I think many people working in our industry at the moment, right, are coming across the distributed systems more and more, whether they're using them, whether they're like yourself involved in implementing them. I mean, whether that's for telescopes, or whether that's for point of sale solutions, or whatever it is in the always on world that we're in. How would you sort of recommend? What would you recommend someone who is interested in going a little bit more deeply into this? How would you sort of recommend them to proceed, to go forward?
Yeah. So one of the goals for this patterns work as well was that someone reading this material should be able to navigate open source code bases. And I think following open source products and going through their code bases, trying out, maybe isolating some pieces of it and playing with it. I think that's a great way to learn about distributed. I mean, particularly topic like distributed systems. It's a great way to learn, because if you go down the route of theoretical understanding, I mean, there are a lot of nice books, I would say, but you might get lost.
Right.
So I think it helps a lot to remain closer to code while you are learning stuff.
One of the things I again really likes about this is it opens up a whole new set of patterns to a whole new generation of people, I think, right? So, and because as you say that because they are patterns, because there is code there, it gives us another set of tools, or rather, it exposes the tools that have been there, but that have been used by systems engineers generally, right? And I think that is, I mean, obviously my background is in, I would say, sort of distributed systems, in terms of microservices and that kind of thing.
Yeah.
But not at, I mean, I've implemented some of these patterns myself, and but we are probably in the minority, right? But that's the thing. What's really useful about this is it's opening these patterns up to a much wider audience and making them available.
Oh yeah, absolutely, I would say. So like something as widely known, but not well understood as two-phase commit. I think
Starbucks does anyway.
Yeah. So I have documented two-phase commit in here as well, and some of the nitty-gritties of what might go wrong and how it's solved in modern implementations. And knowing something like that, I mean, these scenarios come in your microservices implementations as well. I mean, at a different level of abstraction, obviously, but or things like idempotent receiver. I mean, I have a pattern called as idempotent receiver, and it's I think in any microservices implementation you will need that, and getting some clues and ideas of how, let's say, Kafka and etcd implements this idempotency. It opens up.
It opens up a whole new set of approaches. Because I mean, we talk about idempotency a lot, but then people it's one of those things that people forget to implement, and then go, but there was this thing I forgot. It's called idempotency.
Oh yeah, absolutely. Absolutely.
Okay, so I guess we should sort of think about what's next now. One question I had: what have you found most surprising while going on this journey?
Oh, what's so surprising? I think one of the most surprising things is, I mean, all these things are out there so many years, and there are so many implementations now, at least. But they are not. I mean, I was surprised that these are not well-known things. And like Paxos, for example, taught in academia for 20 plus years, and still you required a new PhD thesis to document something called as Raft. And even before that, there was view stamp replication algorithm, which is exactly like Raft. Just no one knew about. It's so surprising that as an industry, I think these things were not well known. For some reason.
Well, thank you very much. So what's next? Now the book is out. Congratulations, by the way. I think it's destined to become an instant classic. So I mean, I've really enjoyed reading it. It's certainly just opened my eyes, just to say things, because it's so practical, because it's so readable and so accessible. So I think it's a really important contribution you've made. I wanted to thank you. But what's next? What's next for you?
Yeah, I think just going back through some of the patterns, I mean, I see a lot of scope for improvement on some of those. So I maybe will take a stab at improving some of these patterns. And also I think continue. I did a couple of workshops teaching Paxos and Raft and stuff like that. So I'm planning on extending that. I mean, have more workshops where people can actually play with code and try out some of these things.
And are you planning on? I should mention that obviously the original repository of these patterns was on martinfowler.com, or a lot of them. Are you planning on continuing that work as well?
Yeah, I think I will continue on that, and I wish I get time to continue on that.
But we'll look out for you in a workshop near you. And I guess, I mean, go get the book, everyone. It's brilliant. It genuinely is. I just want to say thank you so much, Unmesh, for joining us on GOTO Book Club to talk about patterns of distributed systems. As I say, I think it's destined to be an instant classic and is full of just fascinating detail on how the things that run our world work actually, right? Because that's really what we're talking about here. So thank you very much for joining us.
Yeah, thank you, James, for giving me this opportunity.
No, it's fantastic for me to get the opportunity to talk to you. So, and thank you to GOTO and the GOTO Book Club for organising this. You can see this. Hopefully you enjoy it. Thank you very much.
Thank you.
Subscribe to the GOTO YouTube channel now and join the experts in person or online at any upcoming GOTO conference using the promo code Book Club. Visit gotopia.tech to learn more.